Next up, we have Ms. Tan Ziying from the Alibaba NTU Joint Research Institute program. She will share with us her presentation topic on personalized federated learning. Yeah.
Hi everyone, good afternoon. I'm Alysa. I'm a PhD student from NTU, and today I'll be talking about personalized continuous federated learning. Right, I'll begin the presentation by first introducing some concepts on federated learning, personalized federated learning, and continuous learning. And then I'll discuss a bit about personalized continuous federated learning, PCFL, its goal as well as some of the open research questions, as well as some preliminary work that was done to address one of the research questions. So first, a bit of recap on federated learning. The goal of FL is to collaboratively train a machine learning model on distributed data. So in the traditional centralized machine learning setting, the raw data are aggregated and sent to the server. But in FL, the data are reside locally at the client side, and they are not transferred to the server. But what's transferred are model parameters that are fraction in size as compared to the raw data. And so this makes federated learning privacy preserving and also communication efficient. So the classical algorithm for FL is known as federated averaging. And the FL process consists of 4 key phases. First, we have the client selection phase, where a subset of clients is selected to join the FL process. The global model and the server is then broadcasted to the clients, and each client will then train its local model on a few number of epochs to converge the local model. And the local models are then sent to the server for aggregation. And this repeats for a certain number of communication rounds. So here are just some trends on how federated learning is becoming popular, both as a research topic as well as in commercial settings. So in Google Trends, we can see that the number of search queries for federated learning has increased over the past 5 years. And also Gartner has listed FL as an emerging technology that has a lot of potential for growth for the next 5 to 10 years. However, there are some performance issues with vanilla FL. And the first thing is that the model does not converge well when the data is not RED. So in federated averaging, the server updates, they move towards the average of the client optimal. And so when data is RED, the average model is close to the global optimum. But when data is not RED, the average model will be far from the global optimum. And secondly, federated learning trains and makes inference from just a single globally shared FL model. As such, if the local data distribution is very different from the global distribution, the global model will not be able to generalize well. So there's a subfield of FL that's known as personalized FL that addresses the 2 key issues that were mentioned earlier. And PFL is an emerging area that's becoming popular. And we have a survey on this topic that was published on TNLS, where we provide a systematic review and a structured perspective of PFL to bridge the gap in the current FL literature. We introduce a new taxonomy that divides the field based on its challenges as well as the strategies. So the first strategy is known as global model personalization. Just like in the vanilla FL setting, it assumes a single global model. And the goal here is to improve the performance of this global FL model under data heterogeneity. So first we have database approaches. They try to alleviate the problem of data heterogeneity by trying to reduce the heterogeneity of the data distributions. And there are data sharing, data augmentation, and client selection methods. So the idea for data sharing and data augmentation is to have a more homogeneous distribution of clients. But however, by doing so, they often involve a certain degree of privacy leakage, like the sharing of data samples or data statistics. And the idea of for client selection methods is to sample from a more homogeneous data distribution. We have regularization approaches that aim to improve the generalization of the global model. This is done by introducing a regularization term to the local loss. So we can perform regularization between the global and local models to reduce the effect of client drift. And it can also be done across the different historical local model snapshots. So by increasing the distance between the representations across the snapshots over time, it can help to speed up the model convergence. And next we have meta learning. So meta learning is also used to improve the global model, but it has a goal of fast adaptation or personalization on the client. So in standard FL, the goal is to minimize the aggregated local loss across all clients. But in meta learning, the goal is to learn a global model that performs well on a new task after it is updated with a few steps of gradient descent. But this can be quite a computationally expensive process because the computation of these gradients will require access to second order information. And so commonly for meta learning, they make use of gradient approximations to speed up this, to reduce the computation cost. And next, transfer learning can help to improve the adaptation of the global model to local model. And there are a few works in the healthcare setting that use a similar approach to achieve this. For the second strategy, the goal is to collaboratively train individual personalized models for each client. So architecture-based approaches, they provide a personalized model architecture for each client, while similarity-based approaches, they leverage client relationships to improve the model performance by trying to build similar models for related clients. So for parameter decoupling, the idea is to have a set of private parameters, and these parameters are only trained locally, and they are not used in federated training. So there can be personalized layers where we use only the base layers for federated learning, and we have a few deep layers that are kept private. And there can also be personalized feature representations that are kept private at each client. And an advantage of doing so is that it offers some kind of flexibility, as we can design specialized encoders, especially if we are dealing with different data modalities. And there's also potential to learn fair representations. But there are also a few works that try to learn the parameterization strategy in a more optimal manner. So it's more like the decision to see how we can optimally split the private and federated parameters. So for knowledge distillation, the key advantage is that it allows a personalized architecture design for each client. And in FedDF, for example, it assumes a setting where the each clients require models of different model architectures, as they have different computational capabilities. So for example, we have different architectures like MobileNet and ResNet. So the server constructs a certain number of prototype models to represent clients with identical model architectures. And the first step is to perform federated averaging within each prototype group to initialize the student model. And then they can perform cross-architecture learning. So the client teacher models, they can make inference on the computer response. The logic is based on a public data set. We can use that to train the prototype model in the server using knowledge distillation. So next we have multitask learning. The idea of multitask learning is to train a model involving several related tasks. And this can help to improve the model performance as it leverages some kind of domain-specific knowledge across the learning tasks. And in FL, we can treat a client as a task. So a personalized model is learned for each client while modeling the client relationships to improve the model performance. And the Mocha algorithm is one of the first frameworks that extended the multitask learning setup to federated learning. However, it's only applicable for convex models. And since then, there are several actually. multitask learning frameworks for federated learning. So for example, we have FedAMP. What it does is that it constructs the personalized cloud model for each client server, which is a linear combination of the other client models. And the idea for this is that it tries to enforce a stronger pairwise collaboration for clients with similar data distributions, such that related clients will learn similar models. Next, for model interpolation, it uses a mixture of global and local models to achieve a balance between generalization and personalization performance. So in APFL, it introduces a mixing parameter that is adaptively learned. So this enables the optimal degree of personalization to be learned for each client. In this sense, if the local distribution is very different from the global distribution, we will expect to see a larger weighting factor so that there's a larger contribution from the local model. And finally, we have clustering that allows for group level personalization. So this is relevant especially when there are inherent partitions among clients, or if there are data distributions that are significantly different. And the idea here is to use a clustering method like hierarchical or k-means clustering to first partition the clients. And then a federated learning model can be trained for each client cluster. So we identify a few research directions for PFL, and one of it is temporal adaptability, which is related to the field of continual learning. It is currently understudied, but it is an important area of PFL, as there are often changes in the underlying data distributions in federated systems. So continual learning is a machine learning paradigm that aims to learn from data streams, whereby the data distributions and learning objectives change over time. It models a sequence of learning experiences where the goal is to learn new knowledge from new experiences without forgetting the knowledge that they learned from the old experiences. So there are three key scenarios that are studied in continual learning research. The first is task incremental learning, which is the most simple amongst the three scenarios. So the model solves multiple distinct tasks, and the task is given during test time. So in this example, so say we have task 1 that's given. All the model has to do is to predict whether it corresponds to the first or second class. And next we have domain incremental learning that deals with changing data distributions in the data stream. And unlike task incremental learning, the task is unknown during test time. And finally, we have class incremental learning, where new classes are introduced sequentially in the data stream. And the model is required to incrementally learn on new classes while preventing forgetting of the old classes. Right, there are three main approaches for continual learning. First, we have replay-based approaches that we train the model on a small set of stored samples from the old tasks. So for example, ICAR is a notable work for class incremental learning. They introduced an exemplar management strategy that has been widely adopted by many works. So what it does is that it stores a set of representative exemplars for each class. They are selected using the nearest mean of exemplars. And remind, it stores and replaces a quantized population of features that consume a smaller memory budget. So it makes it more memory efficient. And to avoid exemplar storage, pseudo rehearsal methods, they generate samples in memory on the fly. But the quality of the performance is highly dependent on the quality of the synthetic samples that are generated. For the next class of approaches, we have regularization-based methods that introduce regularization terms in the loss function to constrain weights updates in order to prevent forgetting. So learning without forgetting, LWF, is a distillation method. So what it does is that it computes the responses based on new task images on both the previous old model as well as the current model. And we can then distill the differences between the responses from the old and the new models. So there are other variants of distillation losses, such as a cross-distilled loss, pooled output distillation loss, and also the attention distillation loss that are quite popular. Finally, we have architecture-based methods. They dedicate different model parameters to each task to prevent forgetting. So for example, HAT, hard attention task. It learns a hard attention mask for each task to preserve the knowledge of previous tasks by freezing a portion of the weights. PNN, progressive neural networks. It expands its network capacity for every incremental task and adds lateral connections to the previous knowledge. However, it will also result in increasing network complexity as well as a growth in memory requirement. I will now move on to the next section to discuss more about PCFL. So most PFL works, they assume data stationarity. However, there are often changes in the underlying data distributions in dynamic real-world systems. And PCFL focuses on the training of PFL models on changing data distributions over time, which is an understudied but important area of PFL. So an example of a use case is an IoT system, such as the City Brain project by Alibaba. It implements traffic forecasting algorithms. So there are edge devices such as cameras and radar sensors that are distributed across the highway networks. And federated learning can be used to enable collaborative learning while ensuring privacy in that there is no need for a central facility for data storage. And personalized model, PFL can help in local adaptation of the models to locally occurring situations across the highways. And continual learning can enable learning on continuous data streams more efficiently without the forgetting of the older data. So based on the challenges faced in real-world federated learning systems from data, algorithmic, and system perspectives, we identified 3 open research questions which are important to real-world scenarios in PCFL. So in deployed FL applications, there might be a need to continually adapt an existing FL model to changes in the underlying data distributions, such as distribution shifts or an expanding set of target classes. So for example, an e-commerce company that's expanding to a new region would have a requirement to build a recommender model. Although they have an existing model that's deployed for a different region, the target classes and the data distributions that the existing model was trained on are different. And so this scenario will be quite relevant to PCFL. So we'll look at the problem formulation for this scenario. In PFL, the clients in the FL Federation, they collaboratively train a global model as well as its own personalized model on its own data set that is denoted by TC. So in CL, we consider a sequence of tasks. And for this scenario, the number of base classes is significantly larger than the number of new classes. And we extend the continual learning setting to PCFL, where each client learns on a sequence of local tasks. So we consider the class incremental learning setting, where the model is required to incrementally learn new classes from the new task and predict over all the classes from the previous task. And the classes across the task are disjoint. So in continual learning, the main challenge is to overcome the phenomenon that is known as catastrophic forgetting. As new tasks are added over time, the model experiences a significant performance degradation on a previously learned task. And this is actually an inherent problem in deep neural networks due to its algorithmic design. So there's something known as the stability plasticity dilemma in continual learning, where the model wants to maintain a plasticity that is as high as possible. But by doing that, it often results in some kind of forgetting of the old knowledge. On the other hand, we want the model to be as stable as possible to maintain the old knowledge, but by doing so, it will inhibit the learning of new knowledge. So it's more like a trade-off between the two. So here are some design considerations that we incorporate into the framework. Firstly, we adopt principles of plasticity and stability. So training is done in two phases. The first stage will primarily be prioritizing plasticity, and we'll do that by decoupling the representations of new tasks. And the second stage will be to construct a unified classifier and control the trade-off between plasticity and stability. And the next problem is class imbalance. So in the conventional class incremental learning setting, each task contains the same level classes. But in this setting, the number of base classes is a lot more than the number of normal classes. And so we address this by introducing a new task-weighted auxiliary routing loss in the second stage of training. And to facilitate knowledge sharing, we'll distill knowledge from other clients through FL on a subnetwork in the first stage of training. So the first stage is to train expert models with knowledge distillation. In order to address catastrophic forgetting, we first obtain the pre-trained FL model and freeze a portion of the feature extractor. And for every new incremental task, we create a new branch to learn task-specific features to decouple the representations of each incremental task. Each client then performs local training for a certain number of epochs, and then it sends its subnetwork to the server for aggregation. And in the next global round, this aggregated model is then sent to each client, and then it's used to distill knowledge to the clients to construct a more effective feature representation. So the loss function, the local loss function will then consist of both the classification loss as well as a distillation loss. And for that, we use the KL divergence as the distillation loss to measure the difference in the representations between the two different logics. So after the first stage, we have expert models for each task, which is denoted by each network branch. And we need to construct a unified classifier to integrate knowledge from all branches. So in order to enable knowledge transfer across branches to learn interclass relationships, we use a small class balance dataset to learn self-weights. So delta Z here denotes the knowledge transferred from all other branches to branch B. And in order to prevent overfitting on the small data set, we freeze the weights of the backbone expert models. Output is then the sum of the backbone output Z and delta Z. So this setup can help to preserve the core knowledge of the network for stability, while still allowing knowledge transfer across the branches. And in order to address class imbalance, we introduce a task-weighted routing loss to prioritize the classification of novel classes into the correct branch. And recent classes will be given a larger weight within the novel classes to prioritize their performance. So the total loss will consider classification routing losses. And alpha can be used as a hyperparameter to control the stability and plasticity trade-off. So we used the C500 dataset for the experiments and created two different task sequences. The first task sequence consists of 90 base classes, followed by 5 incremental tasks of 2 classes. And the second task sequence consists of 50 base classes and 5 incremental tasks of 10 classes. And for each incremental task, we conduct 5 global rounds of FL training on 5 clients. And for the knowledge fusion phase, we train the local model with 5 epochs. And 20 epochs for the knowledge fusion. And ResNet 18 is used as the backbone of the model. And we freeze the first 3 layer convolution and blocks for stage 1 training. So for fair comparison, we construct exemplars for knowledge fusion using the same exemplar management procedure that was proposed by iCarl. And the exemplar memory for each client is set as 2000 for all tasks. We will compare the results with the following related state-of-the-art approaches for federated continuous learning. So first we have federated averaging, which is a classic method for FL training. and then learning without forgetting, a distillation-based method, ICAR, a class incremental learning method. And in order to mitigate forgetting, we run 3 additional experiments of the above baselines by freezing the first 3 computational blocks that is similar to what we did for the baseline. So here are some results from the experiments. The model outperforms the other baselines quite significantly for both task sequences in terms of the average accuracy across all tasks, as well as the average base and number accuracy. So although learning without forgetting and ICAR are state-of-the-art methods for continual learning, they show good performance in settings where there's an equal number of classes for each task. But when there's a large number of base classes, these methods have a higher tendency to experience catastrophic forgetting on the base classes, resulting in a low base accuracy. But when we try to freeze a section of the feature extractor to promote model stability, the models are able to better retain its knowledge on their old classes. So to analyze the effect of the stability plastic state trade-off for our proposed model, we vary the value of alpha. As the value of alpha increases, a larger weight is assigned to the routing loss to lower the probability of misclassification of novel classes as a base class, because there's a large imbalance of base and novel classes. So with a larger alpha, the model prioritizes learning, and the accuracy of the novel classes will increase. And likewise, when alpha is smaller, the model promotes model stability, and we'll have a better base accuracy. And we also vary the exemplar memory. And you can see that the model is able to achieve competitive performance with other baselines with a lower memory footprint. Next, I will discuss 2 other research directions. So our research direction is to enable the training of PCFL models in few-shot settings. Data scarcity is the core motivation of clients who join FL, because they are often limited by their capabilities to train a good-performing local model. In the class incremental learning setting, clients will be required to incrementally learn new classes from very few labeled samples. So the challenge lies in the significant overfitting problem arising from learning from a small amount of data from new classes. And at the same time, such learning will also worsen the catastrophic forgetting problem in continual learning. And the next research question addresses memory and communication efficiency in PCFL. In complex edge computing-based FL environments, there's a significant variability in hardware capabilities in terms of memory, power, and network connectivity. So while optimizing for model accuracy in PCFL, there are often trade-offs in terms of system scalability, which includes storage and communication overheads. And in order to address forgetting and continual learning, many approaches require a memory budget for storing of old exemplars, but it may not be very applicable to client devices in FL that are more memory constrained, as they generate streaming data over a long period of time. And besides, there are also potential privacy risks from long-term data storage. And this is especially prevalent in the healthcare industry, where there are legislations that restrict the long-term permanent storage of data. And finally, there is also a need for communication efficient mechanisms to address bandwidth challenges in FL. That's all I have. Thank you.
Thank you, Alysa. Take a few questions from the audience, if there's any.
I think it's towards the end, the slides, right? Because you're talking about the future direction in terms of the memory, and the storage and the communication bandwidth, right? Currently, may I know how far you're looking into this period in terms of the computation system? You're using a GPU, or you're using a NPU to do this, and what kind of memory constraint level you're talking about?
So for this, in terms of the memory, it's more of the, so like in continuous learning, typically you will make use of, you will store a certain number of old exemplars, or like old data. So it's more about, in terms of data storage, rather than the CPU memory, the memory of the computer.
So this is still CPU based. This is not GPU or accelerator.
Yeah, GPU was as well, but I'm talking about the physical memory in terms of not so much about computation, but more like the storing of the data itself. So the thing about continuous learning, if you want it to work well, many of the approaches they physically store the old data. Yeah, but for federated learning approaches in general, it may not they may be it may not be so applicable to assume that there's a memory budget for that.
Right, because for a long period of time, people are doing pruning and all these things to reduce the size so that you're able to do it at a constrained device, pruning. They're doing a lot of pruning.
Oh yeah, right.
Yeah, so you're not doing any pruning, you're just keeping all this stuff as it goes along. So it'll be humongous when you, even for GPUs, you're going to, yeah.
So pruning is one aspect, but that's more in terms of the space that you allocate for the model. But that's more about data storage. But of course, pruning can also be a potential direction. But model pruning is something that is more. I guess it can be a possible direction as well, but it may not be as related to as in for this direction specifically, it's more about to address the limitation of having data storage in continuous learning.
Right. So my assumption is you're using ANN, the typical normal way of doing it. It's not using the SNN, the brain way of processing.
Yeah, it's just using ANN, I guess.
Okay.
It's ANN.
Okay, because there's another paradigm to, if you go to spintronics and you move towards SNN memorister kind of model to actually convert into that model, and you may be able to constrain down your memory size.
Yeah, for that it can definitely be like stackable and add on to like what is currently being done to like all the models we have so far. But that is of course like a different direction of research. So it's more like the model pruning stuff, more like how do you make the model architectures more compact and memory efficient. But that line of work can be applied to any of the deep learning models, I would say. Is that?
Thanks.
Thanks for sharing. Can you introduce something more about how you construct the test cases in the results you just shared?
The test cases?
Yeah, so for example, how the test data is formed and how the accuracy computed for each of the clients. Yeah, thanks.
Yeah, so the test set is already initialized, pre-constructed in the CIFAR 100 set. I think there's already a certain partition for train and test images. So, but what I did for the experimental setup, because it's a class incremental learning setting, so every task will have a different set of classes. So for this case, for example, if we look at, say, the second task sequence, there are 100 classes for this data set. We have 50 classes as the first task 0 actually. And for the next, and then there will be 5 incremental tasks of 10 classes each. So the classes are disjoints across the tasks.
So, do you mean that for all the clients, they will have the same test data, test cases?
For all the clients, so for this case actually it's still a bit more towards ID. So there's like, what I did was just to split the data across different sets, and then like each client will have like, let's say like we have 5 different, we partition the data like into 5 splits, and each client will have 3 out of 5 splits. Yeah, but I'm actually working on a more challenging no-ID setting. Yeah,
Yeah,
they already share results with it.
Yeah, because I'm thinking you're doing personalized FL, so I'm thinking whether the test data of each client is different from, the distribution is different from one to one. Yeah, that's why I'm asking this question. So the accuracy is still computed on the test set of each client, then average over all clients, right?
Yeah.